Okay. Welcome everyone to this first Women in Network Science seminar. First, if you are a Python person, because second for our people, because we had a meeting last week where we were talking about the Women in Network Science Society, what were the previous projects, and what are the future steps. So today is the first talk with a speaker for the fall 2023 edition. So our speaker today, first, thanks Clara for being here, for accepting the invitation. And so the speaker is called Clara Stegehuis. She's an assistant professor at the Twente University in the Netherlands of the Mathematics of Operation Research Group. And she earned her PhD in 2019 at Eindhoven University of Technology. And the title of this talk is Network Motifs, Where Can We Find Them? So I will leave the floor to Clara, and just to tell to everyone, there will be time for a question at the end. So you can post them in the chat or just at the end talk. Okay, so Clara, here you go.
Okay, so thank you very much for inviting me. Of course, if you have any questions during the talk, feel free to ask them in the chat as well. And if I see them, I can, of course, already start answering them. Or if something is not clear, feel free to speak up and say so. So this talk is about network motifs and where we can find them. So because it's a bit of an interdisciplinary audience, I try to make the talk as not so mathematical as possible, but still, if you feel lost or if you have any questions on what the more precise results are, also feel free to ask, of course. So I think everybody here probably knows what a network is, but I still have some examples of networks that you usually find. So networks, of course, appear in many different places. You have social networks where people are connected through their social connections on social media. Networks where nodes represent people and edges represent collaborations, for example. But also completely different networks where nodes can be proteins and edges can represent whether two proteins can interact together. Now, so of course, these networks, we all know that these networks can have some properties that are very similar. So there were, of course, many networks are very large, for example. They are usually quite sparse, so the average degree is not so large. So in some sense, many networks have very similar properties, but there's also ways in which different types of networks are actually very different. And one of the first properties that was documented that in which networks seem to be quite different is in network motifs. So I guess approximately 20 years ago, the first network motif paper appeared. And what it basically did, it looked at a few different types of networks and it started counting small subgraphs or patterns in the network data. So here are some examples of subgraphs that you can think of. So for example, you can think of a triangle is a small graph, but you also have more complex subgraphs on a few nodes that are connected in a small pattern. And what some researchers found in 2002 is that in particular network data, usually there's a different type of subgraph that appears very often. So maybe some networks have many triangles, but some other types of networks have different types of these types of subgraphs. And then, of course, the question is, why does it appear that some networks have more triangles, some networks have some other structure that is important for collaboration networks, for example? And it turned out that in many applications, actually, people were, after seeing which subgraph appears very often, they could relate it back to the specific function of the network. So here I have a few examples of some network motifs that have been found recently or less recently. So for example, on social media networks, some researchers found a few years ago that some specific types of subgraphs are very much correlated to whether there's spam or spammers in the network. Whereas in scientific collaboration networks, some types of motifs of authors that collaborate with others were very much linked to how productive the scientific author will become. And some other types of subgraphs have, for example, been found in protein-protein networks, where they say that if you see these types of network motifs appearing, then it seems that the network is more resilient to damage. So network motifs are what, at least there's what I think of as a network motif. That is, if you find a data set and you find some specific subgraph that appears more often than you would expect, then you can say this is a network motif. But this is already not a very simple definition, because, for example, suppose that we have these three data sets. So I have three data sets. One is about words in the book David Copperfield. The other one is a social network. The other one a collaboration network. And here I listed the number of triangles, claws, which is another subgraph, and a cycle, so like a square. And then you can wonder, okay, now suppose that I count in this David Copperfield book, I have 284 triangles. Is that more than I would expect? Or is that maybe less than I would expect? Or maybe it is exactly what I would expect. And the same, so we see in this David Copperfield network, we only have a few networks, but in the cats or social networks, we have many more. But of course, what you would expect, you can't just give a specific number and say, I will always expect 200 triangles or 15,000. So this, of course, depends very much on what you would like to compare your network to. And it also depends, of course, on the network, on many properties of the network. So, for example, it depends on the network size. If a network is larger, you expect more triangles. The average degree, if a network has more connections, you also expect to see more triangles, or actually any other kind of motif. So there are many parameters that actually influence, like, what do I actually expect? What is the baseline of what I would expect to see? Is the baseline 200 triangles? And I think that 284 is much more than I would expect. Or would the baseline for the David Copperfield network already be 500 triangles? So what people often do is they compare the subgraph count in a specific network data set to the subgraph count in a random graph model, which is also sometimes called a null model. So you have a network data set of where you count 250 triangles, for example, and then you make random graph models that should be somewhat similar to your data, and then you can again count how many triangles do we see in these data sets, the generated random graph ones. And then what often happens is people calculate the z-score. So what that means, so I have the number, so H is a specific subgraph. So let's say we are talking about triangles. So I know how many triangles appear in my data. I can count that. And then I generate all these random graph models, and I count again the number of triangles. And then what you can then do is say, so how much more triangles do I see in my data set compared to what I see on average in this random graph model. So if this value is larger than 0, then I see more triangles than I would expect. And if it's lower, then it's fewer. And usually we also divide by the variance of what you see in a null model, because if in a null model you see a huge different varieties of triangle counts, then it's also more likely that what you see in your data is maybe just because of random fluctuations that are there. And the intuition is that this is somewhat related to the fact that you assume that in your null model, you would expect that, for example, the triangle count would follow a normal distribution. And what you actually are saying is, I want to know in my data is my data around the average value of this distribution, or maybe very far away, which is very unlikely. So, so this is the intuition of what you do when you want to find out what is a motif. But then, of course, yes. But then, of course, the question that still remains, okay, so what kind of random graph model do we use at all to see what kind of motifs are significant? And at least when I have been looking through the literature, what I found is that the most often what is used is the so-called configuration model. So that means that if you have a data set, you basically extract what are the degrees of all the nodes. So here I just ordered them in a circle. So here, suppose that I have a data set where one node has degree 4, one has degree 3, and a few have degree 2. Then this configuration model is basically that is a random graph model that creates a random graph which has the same size as your data set and also the same degrees. So you connect them randomly, and for example, it generates a network, for example, like this, but it's random. So it could also look like this, for example. So this configuration model creates random graphs with the same degree distribution as your original data set. And this is already quite useful because we saw already that, for example, the size of your data set already influences very much how many triangles you would expect to see or how many other types of subgraphs. And this already makes sure that the networks you generate have the same size as your original data set. And one choice of the degree distribution that we as mathematicians very often make is we say that we assume that the degree distribution follows some sort of power law or another heavy tail distribution. And this is one reason is because it seems that for many networks, the degree distribution has some sort of a heavy tail, whether it's exactly a power law or not, that can of course be debated. But still, you see in many networks that there's a lot of nodes with very low degree, but also usually a few with very high degree. And one way to model this is to assume that the degree distribution follows some power law. So that the probability that your degree is k scales as k to the power minus tau. Now, what would be useful is, so if you want to find out, so if I want to find out if I have a data set, is this specific motif significant or not? Does it appear more than expected or not? What would be useful is if we just have a mathematical expression which says that given a subgraph square, for example, how often do I actually expect to see this square? Because usually what is done in practice is that you actually have to generate all these null models and count the amount of squares, for example, to see what I would expect. But we as mathematicians can of course try to see, can we actually just get an equation to see how many squares for other types of subgraphs would I expect? But it turned out that in the case of these power laws, where you have some nodes with very high degree and some nodes with also very low degree, this was kind of a difficult question. So it turned out that if we actually ask a more difficult question, which is, where do we actually see subgraphs? Then the more easy question of how many do we actually expect to see was also easier. So what do I mean with where do I expect to see a subgraph? Because suppose I'm interested in these squares. Of course, if I find a square somewhere in my big network, the nodes on which these squares appear have a specific degree. So in this case, degree 4, 3, 3, 5. And it turns out that in very large networks, you can actually almost predict, if I find a square, what are the degrees of the nodes that form the square. And the same with other types of motifs or subgraphs. So it seems that in null models, there's very specific locations in the network where you'll find these subgraphs. So we could actually prove this. So let me just state this theorem, try to state it sort of informally. So it says, suppose that I'm interested in some subgraph H, then we see that in these configuration models, they actually only appear on 4 orders of magnitude of degrees. So sometimes they appear on extremely high degrees. So these are the highest degree vertices in your network. Sometimes slightly lower, and very only if in some cases on very low degree vertices. Now this also sounds a bit abstract, but there's actually for every given subgraph, we can also predict which out of these 4 degrees are most likely to see this subgraph on. And then using this, so if we know where in a network they appear, we can actually also just compute how many subgraphs do we expect to see. And the same holds for the average number of subgraphs. So let me just give an example. I hope that this makes it maybe a little bit clearer. So here I listed all subgraphs of size, all connected subgraphs, so possible motif of size 3 and 4. So what this theorem says is that, for example, the triangle, you almost always find it on nodes with only degrees approximately square root n, where n is the size of your network. So this is where you almost always see triangles. And the same holds, for example, for these 4 cleaves, as we call them. But if you look, for example, at this motif, it appears in very different types of network configuration. So this one is very likely to appear on one node which has a very high degree, and 3 that have a much lower degree. And the same holds for this one, for example. And we can compute the exact same things for all subgraphs of size 5. So we see, for example, that this subgraph appears almost always again on these square root n degrees. And the same holds for almost all of these ones. But we see, for example, that this one again is more likely to appear somewhere where there's 1 node of very high degree and 4 of much lower degree. So why is this the case? Well, intuitively, there's some sort of trade-off going on. So on the one hand, some nodes are hubs and they have many connections. So if you have many connections, of course, you can form many motifs because you just have many connections. So it's quite likely that one of them will maybe form a triangle or another graph. But on the other hand, we know that these hubs are also very rare. So it's also not, in a sense, it's also not beneficial to include many hubs in your motif because there's only so few of them and there's many more low degree vertices. So because of this, what you see actually is that if you have subgraphs which are dense, so which have many connections, that then you often see them on sort of middle degrees. So because you want to see many connections, but you also actually need 5 vertices. So you don't want to have the hubs because there are only a few of them, but you also want not very low degree vertices because very low degree vertices are not very likely to all connect together. And then if you have a subgraph like this, then here it's actually beneficial that there's, for example, 1 hub, which is very rare, but you only need 1 of them. And this hub is very likely to connect, for example, to these 4 low degree vertices. And these low degree vertices, there are so many of them that there's actually many motifs that look like this. Of course, it's not maybe very likely that these 2 connect, but still it happens sufficiently often that you see that this subgraph almost always appears in this shape. So, okay, so this is very nice. And what we can now also see is that here actually, so what I wrote here, this is actually, so how many complete graphs of size 5 do you see compared to the network size? So n to the power this thing. And here we see, for example, different exponents. So for all of these subgraphs, we can see how often do they actually appear in this configuration model. And we can do the same, of course, for these things of size 4. Now, what's, of course, so, but the only thing that is a little bit difficult is that the configuration model is not a very realistic network model. I can already spoil that. I will talk about it a little bit more at the end, but it's not a very realistic network model. So if we just compare what is predicted in the configuration model to what you see in actual data, it will not match so well because this configuration model is so-called, it looks locally tree-like, we say, so it doesn't have many cycles, triangles, and those things. Whereas we know that in real networks, you actually do see many groups, communities, clusters. So what we did here is what we can do is we can actually order the subgraphs for the ones that appear the most in a configuration model to the ones that appear the least frequent in the configuration model. So what is the ordering of the number of subgraphs that I would expect in a null model? And then here for 5 different data sets, we can see how often does a subgraph appear, for example, in this koala data set, all these subgraphs, or in the Android email data set, and several others. And then what happens is if we can actually see if the ordering of these data sets agrees with the one that we expect in the null model. So what we see here is that, for example, these 3 lines are different than what happens in the configuration model. Because in a null model, you see that a square should appear more often than a complete graph of size 4. But in the pink and the green data set, it appears the other way around. So I would say that this is a different way of being a network motif, because in any randomly generated data set, you would expect that there's more squares than complete graphs. But in these particular data sets, it's the other way around. So I think that this would also be a very good way of quantifying what is a network motif. And if we look a bit about it, for example, this green network is a collaboration network in high energy physics. So in a sense, it also makes sense that in a collaboration network, there's many authors that collaborate with all the 4 of them, which generates a clique of size 4. Whereas to form a square, that's actually more difficult because then there need to be 2 authors that collaborate, and these 2 as well, and these 2 as well, and these 2 as well, but not simultaneously. So this is also, it also makes sense that there should be more complete graphs than square in these types of data sets. Now, one thing that I already said a little bit in the beginning is that all these comparisons of the null model to network data sort of assume that if you look at a network null model, the number of subgraphs follows sort of a normal distribution. And we looked at it a bit, like if we generate this configuration model and count, we just generate it a lot of times, maybe 1,000 times, and you just see how many subgraphs do I see. Does it actually follow a normal distribution? And you can see that in some cases so for example here for the triangles, you see that you could say that it could be a normal distribution. It's not unreasonable. This is again triangles, but a slightly different parameter regime. Does not look exactly like a normal distribution, but still at least, well, yeah, it doesn't look exactly like a normal distribution, but it's also not too far off. But if you look at a different subgraph, in this case wedges, here you can see that it's really not concentrated at all. This doesn't look like a normal distribution at all. So you see that in many cases you only see a few of them, but there's also cases in which you see many, many more of them. So in this case, actually, the assumption that you, if you try to figure out what is a network motif, which ones are significant, you can't really assume that there's an underlying normal distribution. So what we can show is that it actually, whether there is a normal distribution, whether there is such a very skewed distribution as this, we can actually exactly show for which types of subgraphs you have these very skewed distribution that do not look like a normal distribution at all. So in summary, if you want to find out which ones have do not look like a normal distribution, then these are the ones that have these purple hubs in the solution of that we had before. So if we look at where in the network am I likely to find this, if the answer is that this is a subgraph that I very often find on hubs, then the answer is then if it often appears on the hubs, then it will the distribution will look like this and will not be very concentrated. So I already said before that this configuration model often generates networks that look almost like a tree. So you will see a few triangles, you will see a few cliques, but not so many of them. And we know that this is really unrealistic. So in real networks, of course, we have many triangles. Friends of your friends are also very likely to be friends as well. So one explanation that is very common these days for explaining why there should be so many small loops in networks is that there's some sort of geometry. So that means that actually everyone in the network has some properties. So in a social network, of course, it could be age, location, interests, or many things more. And then how likely you are to connect actually depends on these properties. So if you are more similar to another person, so if you have the same age and you have the same preference for dogs, then you're more likely to connect than if you are completely opposite. So this means that for all these features, so location, age, whatever, sort of put you in a geometric space that say, I have this age and this is my preference to dogs. But of course, there will be many more. So you can have many properties, and based on how similar you are more likely to be connected. So this is why you are likely to see triangles like this, but not so likely to see them like this between people who are very dissimilar. Now, one model that we use for this is the so-called geometric inhomogeneous random graphs. It's here in equations, but I will also just show it pictorially. So it just means, so we have n vertices, and each of them has a weight. And you can see that the weight is also, you could say that the weight is actually equal to the degree of a vertex. So if in your data set you find a vertex with high degree, you give them high weight. And if you find one with low degree, you give them low weight. And then we say that also every vertex has a position somewhere based on all these features. And then you are more likely to connect with vertices with high weight, but also with vertices that are just very similar, so which are very nearby. So then you see that if a vertex has very high weight, it has many connections, but vertices with low weight often connect only to other vertices nearby. And this is a more realistic model of a network where you have not only the degree, but you also incorporate that people are just more likely to form groups based on people that are similar to them. Now, we wanted to again say, okay, now we have a more realistic model of what a network should look like. And can we then again say, how many subgraphs do I expect to see in this null model so that I'm able to compare it to real data? And now then we again wanted to ask because this is again a difficult question, then the question is also, can we also see in a network where can we actually find all these subgraphs? So in this case, what do I mean with where can I find them? So one is on which specific degrees of the vertices can I find a square in this case? But also, how far are the connections in this so-called geometric space? So how similar are the vertices in a square? Are squares usually formed between four vertices that are very similar in their properties, or are they usually formed between completely different nodes? And again, we could show that that you almost always find these subgraphs on very specific degrees and locations. So for 1 degree exponent, we, for example, found that, for example, this subgraph is very often formed between nodes that have very low degree, so maybe only degree 2, well, not 2, but let's say degree 10, or but definitely not 1,000, and that are very, so they have a small distance. So these are very similar nodes with very small degree. Whereas some others are formed by hubs which are very far away from the other vertices. Now what we can say is that these specific subgraphs are all subgraphs that are only formed by very nearby vertices. So we can say that these ones are actually the subgraphs that you see in the realistic geometric networks, but you don't see them in the networks, null models, which are not so realistic. So for example, we see many squares here, but not in this configuration model that we had before. The interesting thing is that if you start playing around with the degrees, it appears that sometimes these geometric subgraphs are not so geometric anymore, but are formed between vertices of very high distance if you have different degrees. So where in the network you can find specific subgraphs seems to be very complex if you have these realistic networks. So how does this work? Well, so we already had before that we usually have a few vertices of high degree, which can form many subgraphs because they have such high degrees, but there's only a few of them. So on the other hand, it can also be better to include lower degree vertices because there are so many of them. So because there are many of them, they can also create more combinations of vertices. And the same holds for these distances, because on the one hand, you're more likely to connect to close by vertices. So in that sense, it makes you more likely to form a subgraph between nearby vertices. But on the other hand, usually there's only a few vertices nearby and many more far away. So in some cases, it may be actually beneficial to connect the vertices which are further away to create this motif. And so you could say that one way, and then of course there's also still a trade-off between these two. So you can either form many connections because you're just very popular, so you are a hub, and because of this you can create many connections, or because you are very similar to others. And the differences here is that you see that in some cases, all these motifs are formed between similar vertices, and in this case, they are formed by more popular vertices. So it seems that this shows that in these network models, there's two ways to create a subgraph. Now, another question is, what about real-world data? Because we show that some cases you're more likely to find, for example, these things, but also triangles on vertices with low degrees and sometimes on higher degrees. But then we usually see that triangles appear more likely on some middle degrees, and you don't find them just on all possible degrees in your network. And it seems that in real data, there's, at least I got one experiment from someone who did this, is that if you look at in real data, so how often do I see a triangle on vertices with what degree, that there's again that triangles often appear on basically some sort of middle degrees. Of course, you will find triangles everywhere in your network, but you're more likely to find them on these middle degrees than on much lower degrees. And this is actually, in a sense, in agreement with what we found, is that there's a specific degree somewhere a bit in the middle where you are more likely to form triangles than on other degrees. Now, the final question that I will go into today is then, how can we actually use this knowledge to find subgraphs? And because if we know that we know where in a network we should be able to find these subgraphs, then can we actually use this to find them faster? And here we did some experiments, so I will not explain it in a full detail, but so we looked at cycles of size k, so the subgraphs were just cycles of size 4 or larger. And here we can see the success rate of the algorithm in finding them. So we proposed several algorithms, but the main thing is that often, so we predicted that in null models, triangles almost always appear on degrees which are roughly equal to the square root of the network size. Now, it turns out that in real networks, often the square root of the network size doesn't work so well. But what does work very well is some other middle exponent. So not the square root of the network, so n to the power 0.5, but in this case, n to the power 0.4. If you do that, then our algorithm very often succeeds to find these cliques. But the unfortunate thing is that in other types of data sets, it's maybe not n to the power 0.4, but n to the power 0.3, or n to the power 0.2 even. And here again, n to the power 0.4. So it seems to be the case that in real networks, you also often see specific motifs on very specific degrees. And if you know on which degrees, then of course you can use this to also find them more efficiently. But of course, before that, you already have to know on which degrees they appear. And for that, I can't really offer any advice, but it does seem to help, especially compared to this is where you actually look through the entire network, and that is often much more computationally expensive. So the conclusion is that, one conclusion is that if you are looking for network motifs, whether they are significant or not, depends very much on which null model you use. So do you include the geometry? Do you use the configuration model, where you will actually usually see that any kind of motif which has a triangle or another loop is significant if you find only a few of them. Second conclusion is that depending on which motif you are interested in, the z-scores that are based on a normal distribution may not always be suitable depending on the motif you use and the null model. And the final conclusion is that we usually see that subgraphs, so one interesting thing is I want to know how many subgraphs there are. For me, another interesting thing is to see where are they located. And it seems that in many network models, as well as in network data, these subgraphs often appear on very specific network locations. So thank you very much for your time. If you have any questions, of course, feel free to ask.
Thanks for the interesting talk. I think we have a question in the chat first. So Ella is asking if you know about hands-on workshops to find motifs. So for beginners, where should we start?
No, so I think that the literature is a little bit scattered, so it depends a bit on what you want. So if you are looking for code to efficiently find algorithms. There are some overview papers in the computer science literature that see like which, because if you have a big network, then it's not so trivial actually to find all these, to count all these motifs, because there are so many options, and if you don't do it in a smart way, it will take a lot of time. So there's actually some papers with code available there that do that for you. But I have to say, for example, I know that in biology, there's also some more overview papers on what do these motifs actually mean, and which ones have been documented to have some biological meaning, for example.
Yeah, I think we all understood from today that it's not easy to find motifs. So yeah, are there any other questions? I'm checking. Okay.
Yeah, someone has the hand raised.
Yeah.
Hi, can I ask?
Sure.
Yeah. Thank you for a great talk. Really enjoyed it. So one question that I had was for general graphs, dense graphs, there are results known that says that the subgraph statistics do have a decomposition. And then, so for instance, you showed that the triangle density is normal in certain parameter space when you fix some parameters, and then it has a normal approximation, but the other subgraph counts or densities may not have, right? So there are results in this direction, if I know correctly, that depending on the graph structure, which means the overall degree distribution or the graphons, you may have a different distribution than the Gaussian distribution. For instance, you can also see the chi-square distribution. You think those results can be used here when you are in place of z-scores, when you know that the limiting distribution would look like a chi-square or something else?
Yeah, so indeed, so there's many results indeed in the dense case where the average degree is very high. So often these methods fail in the sparse case. But I have been looking into these papers, and I think it's very interesting that already in the dense part, because in the dense part you would almost assume that everything averages out and you would see maybe normal distributions everywhere. And the fact that even in the dense case you do not see this makes me a bit worried about what would happen in the sparse case, because I think there probably even weirder things can happen. But my guess would be that everything that doesn't look normal in the dense case will definitely look normal, like a normal distribution in the sparse case. The other way around, I don't know.
Okay.
But this is what my guess would be.
And just maybe I missed that part. How did you use the z-scores?
So I did not use the z-score. That was just an illustration. So I did not use the z-scores myself, but this is how they are often used. So what we were more interested in is like, is this distribution actually anything close to normal? Because otherwise maybe these z-scores do not make so much sense in the first place, because the average may not be very meaningful.
Mm-hmm. And for the dense graphs, if I can continue asking, do we have, or should I? Okay, just one more question. Not a question, but just a thought. So for dense graphs, there are also something called centered subgraph statistics. So you subtract the conditional expectation of that subgraph indicators, and those centered subgraphs are Gaussian, can be approximated by Gaussians. So even though your subgraph densities cannot be approximated by Gaussian, for dense regimes, the centered subgraphs can be approximated by Gaussians. You think something of that sort would be useful here?
I don't know. I mean, if it were to hold, I guess, I don't know if something similar would hold for sparse graphs. I mean, maybe what would be useful is that if you have these power laws, then most of your graph is very sparse, but there is a small region of high degree vertices which is actually dense. So maybe it could work, especially in this dense area where some of these motifs are actually located.
Right.
Yeah, I would have to think about it.
Thank you.
There is another question from the chat. So what made you interested in motifs?
Yeah, so what made me interested in motifs? Well, I don't know, I just happened to be involved in a research project that was only focused on triangles. And then we were thinking, I mean, I was thinking very soon, like, but can we not, why should we focus on triangles? And then I just found the mathematics of all these subgraphs very interesting. And then I started reading also about the applied literature, because what do people actually use? And it turns out that it's actually quite complicated if you want to actually draw conclusions from them. So that is what I found very fascinating. And like I see also foundational literature. I think the beginning would definitely be the paper of, I think, 2002 by Milo et al. I think in Science or Nature or some. So I think in 2002. So that is basically the first paper that actually looked at network motifs in the first place. And after that, of course, many more literature has been there.
I think it's this one. Network motifs, simple building blocks of complex networks, right?
Yes, that one, yeah.
Okay. I also have a question. So about the GIRG, so the model in the geometric space, how would you arrive to the embeddings of the node in the geometric space? What are the possibilities?
Yeah, so indeed. So the mathematical assumption is usually that if you don't have them, you assume that they are just uniform over, positions are just uniform over the space. So that is what we often assume. But of course, if you have this may I think this may probably not be realistic in many cases. So it's, of course, in a sense, I mean, it's better than assuming that there's no geometry at all. But maybe indeed, if you have some extra information, maybe even from just like a machine learning network embedding, then I could imagine that it would work even better.
Yeah, there are tons of
models. And then the question is again which one to use, and yeah.
Thanks. Any other questions? Okay. So if there are no further questions, let's thank Clara again for this talk. And see you next week for the next seminar.